Okay, so last week you guys had the midterm exam. I've graded those. Your grades have been posted online. You should probably have seen them by now. Um, just like any of the other graded work that we have, if you would like to see what questions you got wrong or just review your exam, just send me an email. Let me know, and I'll pull it out of the stack, and I'll bring it to class for you to review during office hours. Okay, so if you want to see what you did wrong, just send me an email. But overall, you guys did pretty well. A few of you struggled a bit, and so if you find yourself struggling, I'm available during office hours to help you out. Please also make sure you're doing the problems assigned in the textbook. Those are intended to give you some practice of the material. Okay, so we will move on into chapter 7 today. And chapter 7 is all about samples and sampling distributions. And before we go on, it's important that that you have your normal table. Okay, we'll make use of the normal z table. Okay, so and make sure you know how to use it as well. So most of you guys did fine on the normal distribution questions, but some of you did poorly on that section, and so it's going to be very important that you can handle questions related to the normal distribution for the rest of the course. And so if you need to review chapter 6, you can go over the lecture for chapter 6 that I recorded. You can go over the notes for chapter 6 that I've posted. You can redo the homework problems from chapter 6. It's very important that we can handle the normal distribution type questions, because that's going to come up repeatedly in the future of this course. Okay. All right, so let's talk about samples and sampling distributions. Okay, so the idea is that when we perform statistical inference, we are trying to make conclusions about the population based on limited data or based on a sample of data. Okay. Okay, and so the picture that I draw is that we've got this thing. We're going to call this the population. The population itself is too big to be observed directly. Okay. And so instead of trying to look at the entire population, we take a small chunk out of it, okay? And this picture should also be in your notes from the first day of class. And so we take a piece out of it and we call this piece the sample, okay? We observe the sample. Okay, and based on what we see in the sample, we make conclusions about the population. All right, and so this process is statistical inference. Okay. A lot of times the conclusions we want to make are about what we call a parameter of the population. So the population might have a certain property, and that property is called a parameter. So, for example, if we were talking about a categorical variable, it could be something like what proportion of the population has dark hair, okay? So, example would be the proportion in the population with dark hair, okay? So that would be a parameter. That proportion is the parameter. And we want to make conclusions about the parameter. We want to say, you know, in the population, this percentage of people have dark hair, or this proportion of people have dark hair. And so because we can't observe the population, we observe a sample. And so the corresponding property that belongs to the sample is the statistic. So in our example, if the proportion in the population with dark hair, if this is our parameter, then the corresponding statistic would be the proportion in the sample. And this is called a statistic. So you'll have these quantities that are unknown to us in the population. Those are called parameters, and their corresponding property from a sample is called a statistic. So you'll have parameters correspond with the population, and you have statistics that go with the sample. So you could have the population proportion and this would correspond with the sample proportion. So this is the proportion in the population that has a certain property, and over here this would be the proportion in the sample that has the same property. Okay, and so those correspond to each other. Okay, and so the symbol would be, here would be P, and the symbol over here is P hat. Okay, so this is how we distinguish the proportion in the population versus the proportion in the sample. Okay, this is pronounced P hat. Okay. Other things, you could have the mean of a population. So if you're dealing with a numeric variable, you can deal with a mean of a population. And the symbol there is mu. Okay, and then what would the corresponding statistic be? We would just, this would be our sample mean, right? Okay, and the symbol that we use for the sample mean is X bar. Some textbooks do call it mu hat, but I would say 90%, 95% of textbooks use X bar. Okay, over here we could also have the the standard deviation of a population. And the symbol there is sigma. And corresponding to that would be the standard deviation of a sample, or the sample standard deviation. And what's the symbol for sample standard deviation? S. Okay. So we have all of these things that we're kind of getting at. We're going to just focus in the beginning on proportions, okay? So I can also kind of draw a line. This is for categorical variables. And these things down here are for numeric variables. All right, so far so good? Okay. And we said, when you select a sample and you want to make conclusions based on the sample if you want to make conclusions about the population based on the sample needs to be representative of the population. Okay, so. So the sample needs to be representative of the population. If it is not representative, if the sample is not representative of the population, we say that sample is biased. Okay. And there's all sorts of reasons why a sample could end up biased. And those are they're detailed in our textbook, okay? You know, maybe you just did a bad job sampling, but then there's other reasons. You know, if you call someone, maybe they just say, I don't want to answer these questions, and so they hang up, or you know, you call and then no one answers. And these are reasons for why your sample could end up being biased. Now, one method that should give you a representative sample, it's not guaranteed to give you a representative sample, but it should, is simple random sampling, okay? Okay, and with simple representative sampling, or simple random sampling, every person in the population has an equal chance of being selected. And every possible sample has an equal chance of being selected. Okay, so what do we mean by every possible sample has an equal chance of being selected? So you can think of, you know, like lotto tickets, okay? With a lotto ticket, if you think of the winning numbers, okay, it's just as likely for the winning numbers to be 3, 7, 10, 25, 42, 51 as it is for the winning numbers to be 9, 15, 26, 27, 38, and 40, or whatever, however many, you know, whatever they are, okay? So every possible combination of numbers are equally likely to be the winning set of numbers, okay? So, and that's the case with simple random sampling. So because it's random, it is possible for the sample to end up being not representative, okay? So just because it's random, maybe you accidentally select too many of one group or not enough of another group of people or something like that. That is possible, okay? You know, when when they pick numbers for the lotto, they use a simple random method. It is technically possible for the numbers to end up being 1, 2, 3, 4, 5, 6. That is technically possible. It's very unlikely for that to happen, but it is possible, okay? And so with simple random sampling, you should get a representative sample, but it is also technically possible to get samples that are not representative. Okay. So the way a simple random sample works is that you have a sampling frame, okay? So I'm going to just call to do simple random sampling. We begin with a sampling frame. The sampling frame is ideally a list of everyone in the population. Okay, and so this is actually getting a list of everyone in the population is often very difficult to do. If I said perform a simple random sample of the people of Los Angeles, you would need a list of every single person in Los Angeles, and that's almost impossible to do. Okay, we don't have, no such list really exists. Okay. But anyway, assuming you do have a list of everyone or something very close to having everyone in the population, then you select individuals one at a time at random from the sampling frame. Okay, and then when we say select at random, use a random device. Okay, a random device being something like a computer that generates random numbers, or putting names on ping pong balls or on pieces of paper in a kind of in a tumbler or something of that nature, something that truly randomizes things. Because if you gave it to a person and just said select people at random, that would not work. Okay. All right, and so I'm hoping, so once we've established this idea of working with a simple random sample, we can start talking about what we call a sampling distribution. Okay? So a sampling distribution. So the sampling distribution is the distribution of all possible statistic values for a population. Okay, so that might not make very much sense right now. Okay, so let me give you an example, and we're going to deal with the sampling distribution of p hat. Okay. Okay, so we're going to talk about the sampling distribution of p hat. Okay, so imagine I've got this candy machine, all right? And just imagine that it's a big candy machine, maybe, I don't know, hundreds of pounds of candy pieces, and for this example, we'll do Reese's Pieces candies. Okay, so Reese's Pieces candies, if you don't know, they're kind of like M&Ms. They're these little round things. Okay, and there are three colors. There's orange, yellow, and brown. Okay, three colors of candy. And so let's say we know that in this thing, so we've got all these pieces of candy here. So this is, hundreds of pounds of candy. And we'll say we know that exactly 30% of the candies in this machine are orange. Okay. How can we express that using symbols? We want to say that the proportion of candies that are orange in the population is 30%. What can we say? What is this? What's the parameter that we're talking about here? Yeah, so the parameter is the population proportion that is orange. Okay, so we're going to say that P is equal to 0.3. Right? Is that okay so far? So all I'm saying is that we've got this big machine. So just imagine this big machine kind of like this with a tank of hundreds of pounds of candy in it. Okay? And we know that in this tank of candies, exactly 30% of the candies are orange. Is that okay? All right, and what we're going to do is we are going to take a sample, okay? We're going to take a small scoop of candies. We're going to get exactly 50 pieces of candy. So we take a sample, sample 1, 50 pieces of candy. Okay, and it's random. You know, so we mix up the machine, we get a scoop of 50 pieces of candy. So these are going to be 50 random pieces. Okay. What percentage of the candies in the scoop are going to be orange? What do you think? Okay, so the thing is we're expecting that 30%, around 30% of the candies to be orange, okay? So if 30% of the candies in a scoop of 50 are orange, then we would expect 15 of these pieces to be orange, okay? But let's say I dump them out and I count them up and I only have 13 orange pieces of candy. Is that possible? Yeah, it's possible, right? It's a random scoop, okay? So if I dump them out and I count them out, maybe I only have 13 orange pieces of candy. Okay, 13 out of 50 is then only 26% orange. Okay, so my p hat, the sample proportion, is not necessarily going to be equal to 30%. Okay, we're expecting it to be close, but it could be different. Okay, so sample 1, 50 pieces of candy. Okay, I'm going to say we expect to get about 30% orange. Okay, so so we're going to count how many, and we're going to say x is equal to 13 orange pieces. Okay, so my p hat, this is my sample proportion, is going to be 13 divided by 50, and this is equal to 0.26. All right. So here my p hat ended up being 0.26. Okay. All right, so we gather those up, we throw those back into the machine. Okay. We stir the machine up, we take another sample, sample 2. Okay. We're going to take another 50 pieces of candy. Okay, at random again. All right. What's another possible value for x? Maybe I get 19 orange pieces. Is that possible? Sure. So I get 19, so my p hat there would be 19 divided by 50. I get 0.38, 38% orange. Okay. Does this make sense? Okay. And then I can do this again. Sample 3. Okay, again, I'm going to say n is equal to 50 pieces of candy. Maybe x is 18. And so my p hat would be 18 over 50, or 0.36. And then let's just say we keep repeating this. Sample 4, n is equal to 50. Let's say x, we get 15. So p hat here is equal to 0.3. Okay? And so imagine that we do this over and over and over and over again. Okay? And we keep track of every single different p hat that we get. Okay? Now when we do this over and over again, it's quite possible that we get 13 orange pieces again. Okay, it's possible that we get 15 orange pieces. Okay, a lot of times we're going to get kind of the same repeat count. Okay, do you ever think we'll get a sample with all 50 being orange? It's technically possible, but it's incredibly unlikely for that to happen, right? So, you know, if we're taking random samples of 50 out of the machine, it would be incredibly unlikely to get 50 out of 50 orange pieces, okay? So anyway, let's say we do this 1,000 times, okay? Or maybe 10,000 times. We take a scoop of 50 out of the thing, we count how many pieces are orange, okay? And we do this 10,000 times. And every single time we keep track of the p hat values, okay? We're going to create a dot plot, or maybe even a histogram of all the different p hat values we observe. Okay? And when we look at that resulting distribution of p hat values, that is our sampling distribution. Okay? It's the distribution of all the possible statistic values, meaning all the different p hats that we can get for this population. Does that kind of make sense? Okay, and so I can demo how this is going to look. All right, so let's distribution, here we are, okay. So let me set this. So we're going to say we're going to take 50 pieces of candy, all right. And so here's our machine, okay. In this, you got brown, orange, and yellow, and we know that in the population exactly 30% of these candies are orange, okay. Can you guys see this okay? All right, so I'm going to go ahead and draw a random sample here. Okay, so this is the machine spitting out pieces of candy. Okay, and so we count up how many orange pieces we have. Okay, we got 11 orange pieces, and that means our p hat is 0.22. 22% of this sample happen to be orange. Okay, we only got 11 orange pieces. Okay, we can do this again. Okay, oh, and you can see we put a dot down here at the bottom in our dot plot for 22%. Okay, okay. Coincidence, we got 22% orange again. We got 11 orange pieces, so we got 22% orange, so we put another dot right there at 22. Okay, and then I'm just going to kind of speed this up. All right, so here we have 13 orange pieces, so that's 26% orange, so we get a dot right here at 26. Okay, sample number 4. There were only 8 orange pieces, so we get only 16% orange, and that gets a dot right there. So here we have 19 orange pieces, and that's going to be 38% orange. Okay, and we put a dot right there at 38%. So far, so good with everybody? What's going on? Okay, so we're just And basically, just doing computer simulation. Here, 14 orange pieces, so that puts a dot for 28%, okay? And we just do this over and over and over again, okay? 32% orange, 16 orange pieces, okay? 12 orange pieces, 24% orange, okay? And so we can see, you know, we're keeping track of these. We got 28% again. Here we got 28% again, so we're getting all of these dots, okay? We can kind of speed this up. We can do 10 at a time, okay? So far we've run 10 simulations and we've got 10 different dots here, okay? Here I'm going to run 10 all at once, and so 10 more dots will appear here. Okay, so this is after, so now there's 20 dots total in this dot plot, okay, and we can just kind of add 10 more at a time. So after 50 total simulations, we can see that certain values like 30%, 28%, 32% appear most frequently, but we have gotten things as low as 16%, things as high as 44% orange, okay? Okay. Here's our simulation after 100, or here's our distribution after 100 simulations, and we can start kind of cranking this up. So here's after 200, after 300, okay, and we the dots have gotten so close to each other that they're kind of forming lines, okay. So let me just kind of, we'll do. So this is our distribution after 1,000 simulations. And so after 1,000 simulations, which sounds like a lot, but in reality is very few, okay? To build up a true sampling distribution, you need tens of thousands. So after 1,000 simulations, we start to see some patterns form, meaning that things around 30% in the middle appear most frequently, and things out here in the extremes, as low as 14% or as high as 48%, those appear much less frequently. So here's after 2,000, after 3,000. This is after 5,000. Here's our distribution after 10,000. Okay, and this is it after 20,000 simulations. So after 20,000 simulations, we have this this shape right here. Okay, what does this shape look like? It looks a lot like the normal distribution. Okay, and I can overlay the actual normal distribution on top of it, and we see that the shape of our distribution, sampling distribution, looks very, very similar to the normal distribution. Okay, and that's not a coincidence. That's actually, it's been proven via some mathematical theorem that this is what's going to happen. That if the population is 30% orange, when you take random samples out of the population, we would expect something close to 30%. Yes, it is technically possible to get 50% of the sample to be orange, or it's technically possible that only 10% of the sample is orange. But things like that don't happen as often, okay? It's much more likely for the sample to end up being 30% orange, or 32% orange, or 28% orange, or something very close to 30% orange, okay? Yes, sometimes you'll get more than that, sometimes you'll get less than that, but overall, these kind of values in the middle will appear most frequently, and values on the ends appear less frequently, okay? And even after 20,000 simulations, we never got a sample that was 100% orange, okay? Or we never got a sample that was even 60% orange after 20,000 simulations. I guess it could happen after, maybe 1 million or 1 billion simulations, but, after 20,000 simulations, that had not happened. So I'll copy this into our notes here. Okay. So you can test this out. I'll put the the applet in the notes. All right. So this is our sampling distribution. Okay, so after 20,000 simulations, this is our sampling distribution of the different p-hat values that we observed. Okay, p-hat being our sample proportion. So every time we drew a sample, we got different sample proportions, different p-hat values, and we kept track of them all, and this is the distribution that we see. Okay. Is this okay? All right, and so what we see is that this shape looks a lot like the normal distribution, okay? The shape of the sampling distribution. Looks very much like the normal distribution. Okay, and in fact, there's something called the central limit theorem that proves that this is the case. Okay, so so the math for the central limit theorem is beyond the scope of this course, but the central limit theorem proves that the distribution of p hat will indeed the sampling distribution of p hat will be approximately normal. Okay. And so we're going to take advantage of this, right? And so in the future, we're going to say that we're going to approximate the sampling distribution of p hat with the normal distribution, okay? So we can use this to our advantage. All right, and what we will say is that from here on, we will approximate the sampling distribution of p hat with the normal distribution, okay? Now, the normal distribution, in order to answer any question about the normal distribution, you need two properties about the normal distribution. And what are those two things? You need to know if you need to find a z-score for something, you need to have what? The mean and the standard deviation, right? So we're going to approximate the sampling distribution p hat with the normal distribution. The normal distribution will have a mean, of have mean equal to P. What is P? The population proportion, right? So the mean is going to equal the population proportion. Okay, and that makes sense, right? When we take a look at this thing, we're trying to approximate this sampling distribution. When we take a look at it, we're going to approximate it with the normal distribution. What value are we going to put right at the middle? We're going to put, in this case, we're going to put 30% right in the middle. That is the proportion that exists in the population, 0.3. Okay, so that's the population proportion. That's going to go right in the middle. Okay, so the mean is going to be P, and the standard deviation, it's just going to be this formula. There's really not much we can do about it. Okay, it's going to be P times 1 minus P divided by N inside a square root. Okay, it's P times 1 minus P divided by N inside a square root. That's the standard deviation. Okay, and again, this is an approximation, but it's a pretty good one. So basically what we're going to say is that, you know, this is the actual sampling distribution. The sampling distribution is discrete. It can only take on these kind of whole number values. But we're going to approximate it with this normal distribution, which is this nice smooth hill. Okay? But you can see that they line up pretty closely, and it's going to do a pretty good job of approximating each other. Okay? So let's, using this, let's see if you can kind of answer a question here, all right? All right, does everyone have this down? Okay, and is this okay? Just conceptually what's going on? Okay, so let's give you a question, okay? So again, we're going to say in the machine, it is known that 30% of the candy pieces are orange. Okay? If I take a random sample of 50 pieces of candy, okay? If I take 50 pieces of candy, is it possible that 40% of them end up being orange? Yeah. Okay. What's the probability that I end up getting 40% orange or more? Okay, 40% or more are orange. Okay, if I take a random sample of 50 pieces of candy, what is the probability that the sample ends up 40% orange or more? Does that question make sense? Okay. All right, it's a random sample. Okay, we expect that it's generally around 30% orange. But because it's random, could it end up being 40% orange? Or 42% orange? Yeah, it's possible, okay? So if I take a random sample of 50 pieces of candy, what's the probability that the sample ends up being 40% orange or something more than that? Okay, see if you guys can work this out. I'm gonna go ahead and pause the video, and we'll see how we do. Okay, I know So some of you might look at this and you're like, how am I supposed to even get started? Okay? So the idea here is that we want to approximate our sampling distribution with the normal distribution, okay? And when we try to approximate the sampling distribution with the normal distribution, all right? So this is a approximation of the sampling distribution of p hat, okay? So when we're going to approximate this sampling distribution of p hat, we're going to say that the mean is equal to p and the standard deviation is equal to the square root of p times 1 minus p over n, okay? So this should be in your notes, like right before you wrote this, okay? It should be right there in your notes, okay? So that means our mean is going to be what? What's the mean? It's 0.3, right? Our population population proportion is 0.3, and this also means our standard deviation is going to be the square root of 0.3 times 1 minus 0.3, which is going to be 0.7, divided by 50. Okay, so we're going to have the square root of, where's my calculator? 0.3 times 0.7 divided by 50. So we're going to have the square root of 0.0042. Okay. So our standard deviation is going to be this ugly number, 0.0648, 0.06481. Okay? All right, and so this just becomes a normal model problem. We've got 0.3 right here in the middle. I've got my standard deviation to be 0.06481. And I want to know what's the probability that I end up being at 40% or more. Okay? So you guys should be able to do this part. All right? So I'm going to go ahead and pause the video here again and give you guys a moment to figure this out. You're going to need your z-tables if you don't have those out already. Okay, let's take a look. Okay, so at this point it just becomes a normal model problem, very similar to what you saw in chapter 6. So what we want is, what is the area to the right of 40% here? Okay, or 0.4. So all we got to do is we got to turn 0.4. We got to get the z-score for this, right? So we're going to get the z-score for this is going to be 0.4 minus 0.3 divided by 0.06481. Okay? So this is, we're going to get a z-score. When I punch this into the calculator, gosh. All right, I'm going to have to take that to tech support. 0.4 minus 0.3, which is going to be 0.1. I divide this by 0.06481, and I get 1.54. Okay, I get z equal to 1.54. I'm going to look this up in the table. Okay, so we go to 1.54, and I get 0.9382. All right, so I get the area to the left. .9382. I mean, alternatively, I could have looked up negative 1.54 also. And to get the area over here, I'm going to do 1 minus this, and I get 0.0618. Okay, so the area to the right of z equal to 1.54 is 0.0618. Okay, so Is it possible that the sample ends up 40% orange or more? Yeah, it's possible. What's the probability that happens? That happens with a probability of about 0.0618. Okay, about 6%. Again, this is an approximation here. Yes?
Can you explain where this equation for standard deviation comes from?
Can I explain? Yes, but I don't think it's worth covering in class time. I'd be happy to explain it to you outside of the break. Okay? Is this okay? All right, let's try one more example like this, okay? Just kind of make sure we get the hang of this, okay? All right, so let's say that in the population, 15% of people are left-handed. Okay, so we're going to say in the population, 15% of people are left-handed. Okay, we take a random sample of 200 people. Okay. All right, and I'm going to say, what is the probability that in the random sample, only 12% of the people are left-handed. 12% or fewer, I should say 12% or fewer of the people are left-handed. Okay, so it's random, so we would expect something around 15% to be left-handed. What's the probability that your sample ends up being only 12% left-handed? There's something fewer. Okay, go ahead and take a few minutes to figure this out. All right, let's take a look here. Okay, so when we set up our little picture, okay, we're going to say this is an approximation of the sampling distribution of p hat. We're going to say the mean is equal to p, and the standard deviation is equal to the square root of p times 1 minus p over n. Okay? And so over here we've got p is equal to 0.15, and the standard deviation is going to be 0.15 times 1 minus 0.15 over n, which is 200. Okay, so we punch in all of these numbers. We do 0.15 times 1 minus 0.15, which is 0.85, divided by 200. And we're going to take the square root of this number. And I get 0.025248 or 249, whatever, okay? 25249. So we're going to just take the, whoops, not this. The answer ends up being 0.02. Whatever, whatever it was. 0.025249, okay? The answer ends up being that, okay. All right, so that's my standard deviation, and then so I've got, in my picture, I got 0.15 here, and we want 12% or fewer. Okay, so I'm going to have 12% down here, and I want to shade over here. So my z-score is 0.12, 12%. minus 15% divided by my standard deviation, which is 0.025, whatever it was, 248. Okay, so on my calculator, I just leave that there, and in the numerator I'm going to have 0.12 minus 0.15, and then I'm going to hit divide by answer button equals, and I get negative 1.188. Okay, so when we round to 2 decimal places, I'm going to get negative 1.19. So I have z equal to negative 1.19, and I want the area to the left of that. And so I go to my z table, I look up negative 1.19, and I get 0.1170. Whoops. All right. So there, that's our answer. What's the probability that in the random sample, only 12% or fewer of the people are left-handed? And the answer there is about 11.7% probability, okay? Coincidentally, that's close to 12%, but that's our answer. Just want to make sure this process is okay with everybody. All right, so just to recap, okay, we have the sampling distribution, of p hat is the distribution of all the possible p hat values we can get from the population. We can get when we take samples from the population. Okay, this the sampling distribution can be approximated with the normal distribution. And it's based on the central limit theorem. Okay, the mean is equal to p, and the standard deviation is equal to the square root of p times 1 minus p divided by n. Okay? The standard deviation of the sampling distribution also has a special name called the standard error. So if someone talks about the standard error, that's just the standard deviation of the sampling distribution. Okay, why don't we take a short break here.